So I'm going to review support vector machines that Jamie talked about last week, which is a really useful tool for classification. So the notation is very similar to what I just went over, but now I'm talking about different things. So I apologize for using y's and x's again, but now y is a binary variable, -1 or +1, and we're trying to classify these two categories. And you also have features for each of these observations, and we want to try to separate the feature space using a plane. So if we have 2 dimensions, we'll use a line that might be able to separate the different classes that we observe. And we could use this hyperplane as a classification rule of which side of the plane you fall on is how we'll classify you. So here's the general definition of a hyperplane. And then our classification rule will just be to take the sign of that function. So the sign of that function will tell you which side of the plane you're on. And then we'll use that as the rule to determine what class you should belong to. And then once we were able to find this plane that perfectly separates the data, there's infinitely many planes that you could use. So you want to find the best one, the one that'll create the most margin between the points. So the one that's farthest away from the points that you're using to train on. So we could create or formulate this as an optimization problem. So we're trying to maximize this margin M subject to these constraints. So all these points are classified on the right side of the margin. And then there's a restriction on the size of the betas. And this looks like this. So if we have these blue observations and red observations, so they're all correctly classified. They're on the right side of the hyperplane here. And then this margin, these dotted lines, is the maximum distance you could draw this hyperplane that maximizes that margin. But that's an ideal situation. In most scenarios, you're not going to get perfectly separated data. So you want to allow for some slack. So you want to create a hyperplane that classifies as many points as you possibly can. And you'll have some criteria of how many you want to classify right. So now we have, we want to classify these points using our classification rule, but now we're going to allow some slack. So we want to, so before this was greater than some margin, now we're allowing for a slack variable here so that some could be within that margin or some could be even on the other side of the hyperplane. And then you'll have a constraint on those positive slack variables. And I also skipped a step here and reformulated this another way. So I dropped the M notation because you could just set M equal to 1 over the size of beta. And you could drop that from the equation. Now we're going to just minimize the size of beta subject to this constraint. And it's the same problem. So this constant here that controls how many of these epsilons you can have, this is like your budget. So you have a certain budget of what distance you're willing to allow to misclassify observations. And then looking back at this problem, we're just dealing with linear combinations of the x's and betas. So we could expand this. We could include quadratic terms to try to expand this feature space, because as Jamie showed last week, you had some observations that were in circles, and then one class was the outside circle. If you map this into a higher dimension, it actually becomes perfectly separable. So one idea is to apply functions to these terms that maps this into a higher dimension where it might be separable or more separable than the one it's currently in. And that's the motivation for support vector machines, where you have kernels that will determine the different functions applied to those inner products. So some of the most common ones are the polynomial kernels. So if we just took quadratic terms, this is dimension 2, but you could include even higher dimensions. And then there's also a radial kernel. And both of these are very easy to implement, and there's very fast algorithms for doing both of these. And then you could reformulate the optimization problem even another way. And this one looks very familiar. So this looks just like what we saw with regularization, where you're trying to minimize some loss function, and then you have a penalty term with that. So this looks like ridge regression, but instead of mean squared error, we're trying to minimize this hinge loss. So what this function here does with this positive sign is just the positive part of this. So if this is negative, then it's just 0. And then if it's positive, we include that as a loss. So what's going on here is this yi times fx term is, if that is positive, that means the point's correctly classified. Then in that case, if it's 1 or higher, it's correctly classified. So it'll contribute 0 to the loss. If it's less than 1, it'll be within the margin, so it'll contribute a little bit. And then if it's negative, then it'll contribute a lot to the loss function. And then there's also a restriction on, there's a penalized term on the beta, so the betas can only be so large. And this lambda is a 1 over the cost function. So when you implement this in R, you have to specify what the cost should be. So if you have a small cost, that'll give you larger margins and vice versa. And that lambda, that C and that lambda will determine how big those margins are. So that's another tuning parameter. So you can set this up in the same framework as we did for regularization, and this is kind of where they go when you extend this to regression and using this for other things, is using this hinge loss function.